In this video, we'll be covering a little bit more complicated version of the extreme value theorem. So the function we're going to play with in this example is f of x is equal to 1 over x minus 2. Now, in the last example, what we did was we first took the derivative of this, and then we took that derivative and we set it equal to 0. That provided us with potential critical points. You'll notice in this particular case, if I were to take the derivative of this function, I would have to apply what we call, again, the quotient rule. Or I could identify that this is the same thing as this function, again, the x minus 2, the denominator to the power of a negative 1. And then taking the derivative of this function, I could just simply use a chain rule, which means I'm going to take this power down in front. So I have negative 1, x minus 2, and I subtract 1 from the power, so minus 2 on the power. And then what's the derivative of the inside? The derivative of the x minus 2 function is simply just 1. This provides me with negative 1 over x minus 2 quantity squared. Now again, one more time, to identify critical points, we're going to have to identify where the function is equal to 0 and where the derivative function doesn't exist. So if we try and set this thing equal to 0, I'm going to put a question mark there, you'll notice negative 1 can never be equal to 0. Doesn't matter what I let this bottom piece be, this will never be 0. So that's never going to happen. Then we're also going to identify again where the derivative does not exist. And again, where is it undefined? Well, if that's the case, I'm going to just go ahead and set the bottom equal to 0 and find every value where that's going to occur. Well, if that's the case, x minus 2 equaling to 0 provides me with x equals to 2, and that, again, is the case where it does not exist. That's where we can't have the derivative existing at all. So now with this done, this is a potential value for a max or a min. Now, what's not written here, but I'm going to write in here now, is that we are limiting this function on the values from negative 2 to 1, which tells me that if there's going to be a minimum somewhere, it's going to be at that location, or sorry, a minimum or maximum somewhere, it's going to be at that location. But in this case, because of the extreme value theorem, I can guarantee that this thing is now going to have an absolute max and an absolute min because of the negative 2 comma 1. Well, you'll notice if I try to plug in 2 to the original function. So down here, I'm going to do the same thing I did before. I'm going to plug in my endpoints and all of my critical values. Again, one more time, plugging in my endpoints, negative 2 and 1, and then plugging in my critical values. You'll notice that if I plug in my critical value, that is actually undefined. If it's undefined, it can't be a min or a max. Because again, for it to have a min or a max, it has to be defined at that location. We have to get a y value back. Which means that I'm left to having f of negative 2 and f of 1 having to be my absolute max and my absolute min. If I plug in negative 2, that's actually going to provide me with a 1 divided by negative 4, which is a negative 1/4. And if I plug in 1, that's going to actually provide me with 1 over negative 1, which is just simply a negative 1. Now be very careful here. Which of these two values is larger? This is a smaller negative number, which means that this is actually my absolute maximum on that curve. And this one here then is left to be my absolute minimum on that curve. And again, using the extreme value theorem, knowing that this function, oh wait a second, we didn't identify continuity. Well, don't worry, this function is discontinuous at this location, which means that this particular point is already accounted for it being undefined. You'll notice up here, however, from negative 2 to 1, this function has no issues. There are no values where you can't plug in from negative 2 to 1. So given that f of x is continuous on that interval, we are allowed to apply the extreme value theorem saying that there has to be an absolute max and there has to be an absolute min. Now, if for some odd reason this domain here was changed, let's for instance say that my f of x equals 1 over x minus 2, but my domain was from negative 2 to 3. The extreme value theorem no longer applies. There is nothing telling me that this domain is going to work for this function because this function, again, f of x, for the extreme value theorem to apply, has to be continuous on that a to b set of values. And you'll notice that from negative 2 to 3, it's perfectly fine except for 2. At the value of 2, we are actually going to have a vertical asymptote, which therefore breaks the rules of continuity. So it's not continuous on that set, which implies the EVT does not apply. It doesn't mean that we can't find potential max or mins, but it means that we're going to have to look at deeper into the graph. And you'll notice in this graph, it actually is going to look something like this. 1, 2, there's my vertical asymptote, there's my horizontal asymptote, and it should be looking something like this. So we might actually see that, notice this is going down forever, this is going up forever at the value of 2, so we can't actually obtain a max or a min. It can't happen.